Welcome to Unit 1, Lesson 8, Working with Radicals. So now it's important to recognize that we are changing gears from working with rational expressions to working with a word that sounds kind of similar called radicals. So you can think for now of radicals as being square root symbols with a number underneath them. So for example, when we take some number a and we square root it, that overall thing with the square root and the number underneath it we call a radical. And that means we have certain rules for working with these radicals that will allow us to maybe do some simplifying or break down more complex expressions into different ways. So some of the rules that we can talk about for radicals is that when we're multiplying radicals, it turns out two separate radicals multiplied together give us the same result as if we had multiplied the two number parts together first and then square rooted after. So for example, and you can try this on a calculator, if you find what the square root of 2 is, and then multiply it by the value you get when you do square root of 3, when you multiply those together, you should get the same result as what you'd get if you just did the square root of 6, because 6 is the number that would represent a times b, the two of them multiplied together. So that's an important fact to remember when multiplying radicals, and we're going to make use of that fact. In fact, we're actually going to make use of that fact in sort of the reverse order, and I'll show you in a moment how that works. But it's also important that we have a rule for dividing radicals as well. So for example, if you took a radical and divided it by some other radical, if you had first just taken the numbers inside of those radicals and divided them out and then square rooted after, you'd get the same result. So that's what those rules on the top really mean. And if that was a little bit weird for you to just think of in terms of A's and B's, let's see how that works in terms of real numbers. But as we go through all of these, if we want to be able to simplify them effectively, it's really important that we have a whole bunch of important square root values in mind. And when we talk about these important ones, we're really talking about perfect square numbers. So for example, it's going to be really important that we remember all of these perfect squares as much as possible so that when we arrive at them, we can simplify these radicals into whole numbers. Because anytime we see, for example, square root of 4, we don't have to write it in our next step anymore as the square root of 4. We can simplify it into its whole number answer, which is really just 2. But if we, for example, had square root of 3, well, that doesn't have a nice whole number answer. In fact, it's going to be a decimal that goes on infinitely with a random bunch of terms in its decimal expansion. So in order to properly write the square root of 3, we're literally just going to write in its radical form square root of 3 and see how we can possibly combine it or simplify it along with other radicals. That's a whole lot to throw at you right off the bat, but again, this will hopefully make more sense as we go through examples. So let's see how we're going to simplify. Well, this first one says to simplify the square root of 50. Well, what do we mean by simplify? Well, there's a lot of different things we could try. What I'm going to do is, as I mentioned before, I'm going to try and use this multiplication rule, but I'm going to try and use it in reverse. So I'm going to think of the number 50 as two different numbers multiplied together, because we know that 50 could be thought of as 5 times 10, or 1 times 50, or 2 times 25. So there's lots of ways that I can take the number 50 and think of it as two numbers multiplied together. And if that's the case, then I can take each of those two numbers and break them into a separate radical, where I can make a radical for the first number, or the first factor of 50, and a separate radical for the second factor of 50. Now, I just listed some different possible factors. I suggested 5 times 10 gives you 50, and 1 times 50 also gives you 50. But all the numbers I just listed there, 5 and 10 and 1 and 50, well, those aren't very useful to us in these sorts of simplifying cases. It's going to be much more useful if one of our numbers is a perfect square. Now, I guess one of those, the number 1 is also a perfect square. And if you want, just for clarity, you can even add that to your list, that the square root of 0, for that matter, is equal to 0, and the square root of 1 is equal to 1. But that's not really going to help us make this number 50 any simpler, because we're still going to have a square root of 50 that we have to deal with. So a different combination might be 2 and 25. Now again, if you're wondering what's so special about 2 and 25, well, let's think for a second. So I've rewritten square root of 50 as the square root of 25 times 2. So suddenly the 25 and the 2 kind of become like my numbers a and b, which means I can now break this up into two separate radicals. It's the square root of 25, and maybe you see now where I'm going with this, multiplied by the square root of 2. Now the square root of 2 is one of those radicals, like I mentioned before, can't be simplified any further. It's just the square root of 2. And in fact, if you try and punch it in on your calculator, you'll see that it's just a weird, really messy looking decimal number. It's about 1.41 something, but then the decimals go on infinitely from there. So to write it in a nice exact form, we're going to leave the square root of 2 as literally the square root of 2 in its radical form. But square root of 25 is just 5. So our final simplified way of writing this rational is to say it's really 5 times the square root of 2, or 5 root 2 is sometimes how we would say that in a simpler way. Because it is the square root of 25 multiplied by the square root of 2, but because the square root of 25 can be simplified, it's really just 5 times the square root of 2. And what's interesting about that is if you were to play around on a calculator, for example, if you type in the square root of 50, you'll get a certain number. Keep that number in mind. Then try doing the square root of 2 and then multiplying your answer by 5. Well, you should get exactly the same result as when you just directly did square root of 50. So we're really just writing the exact same number in a different representation. That's what this simplifying has done for us. Let's try another one. Well, now we've got the number 20. And again, there's different ways we could break up 20. We could do 1 times 20, or we could do 2 times 10. But we already know the 1 times 21 isn't going to make things any simpler, for the same reason that 1 times 50 wouldn't have made anything simpler. And 2 times 10 isn't that helpful either, because the square root of 2 and the square root of 10 don't have nice whole numbers. But there's another combination that works. Of course, we could call this the square root of 4 times 5, which means it's like the square root of 4 multiplied by the square root of 5. And notice that when I'm multiplying the two separate radicals, you can just write them squished right beside each other. And the fact that we don't see an operation in between them means that they are multiplied together. But now square root of 4 is something with a nice whole number answer. So this is really just 2 times the square root of 5. Or again, we would just say 2 root 5 in a bit simpler way, which literally means that the square root of 20, the decimal number, for example, that you would get when you do square root of 20 is exactly the same as the decimal number you would get if you first did square root of 5 and doubled it, multiplied it by 2. So again, we've arrived at a different, and in this case, slightly simpler way to represent these radicals. And we would say that this is simpler because the simplest form that we can write a radical in includes the smallest possible numbers underneath that square root symbol. So we only want our simplest form to include the smallest possible radicals we can. So we started with a radical of square root of 20, and the only radical involved in our answer is a root 5. So we have made it simpler in that sense. Let's try a little bit faster now. You can pause it at this stage if you think you have an idea for how to split up 54. But if you're a little bit stuck, what I did was break it up into 9 times 6. The reason for that is because when I now break it up into separate radicals, square root of 9 is simply equal to 3. And so this is 3 root 6 in its simplest possible form. Because again, square root of 6 is not something with a nice exact answer. That's as simple as we can make that radical expression. 48 is one that has lots of combinations. And some of them, for example, like 4 times 12. 4 times 12 does give you 48. And the number 4 can be easily square rooted. So 4 times 12 is something that could get you in the right direction. But then you'd have this number 12, or the square root of 12, that you would need to break up even further, because 12 has its own factors that may include ones that can be simplified. So when doing this, always try and find a combination that produces the largest possible perfect square available. So 4, I mentioned, would be one perfect square that's available if I did 4 times 12. But 48 also has other factors like 16 times 3. And I'm going to use this one, oops, not plus 3, times 3, 16 times 3 in this case, instead of doing 4 times 12, because now 16 is an even larger perfect square. So try and find a combination that gives you the largest possible perfect square number as part of your factors. So now I can say it's really root 16 multiplied by root 3, or because root 16 is really just 4, this is 4 root 3 in its simplest form. Now let's see how that division rule can help us as well. That's how we're going to simplify some of these in part B. So remember, our division rule says that if we have a radical on top of our divisor and a radical on the bottom as well, we can just divide the two things inside of those radicals, the two number parts, and make that into one overall radical. So another way to think of this is that it's the square root of whatever we get when we do 48 over 6. Well, 48 over 6 is something we can evenly or nicely divide out, so it's really just the square root of 8. And it might seem like we've made that as simple as possible, but then you always need to take a look and ask yourself, can this number 8 be broken up into any factors that can themselves be square rooted? And in this case, 8 breaks up into 4 times 2. So I could break this up into root 4 times root 2, or in its simplest form, it's actually 2 root 2. Let's try another one. Here we've got root 225 on the top and root 3 on the bottom. Well, let's do the same trick to start that we did in the last one. We're going to make this one great big giant radical with the division going on inside. 225 over 3 is all going on inside the radical. And that's okay because it actually breaks down nicely into a whole number, 75. And now we need to think, can 75 be broken up in any sort of way that produces a nice perfect square? Well, you might remember that 75 is a multiple of 25. It's 25 times 3. So it's like a root 25 times a root 3, or that's like 5 root 3 when I square root the root 25 that I actually am able to. Let's try another one now. Here we've got 2 root 5 on top and the square root of 180 on the bottom. So right now the top is a combination of whole numbers and radicals, and the bottom is just a radical. So I don't want to right away try and do any dividing of the top and the bottom. What I'd like to do first is see if I can change the bottom radical into something that's a combination of whole numbers, and if possible, something on the bottom that will also include a root 5. Because if something in my denominator also includes a root 5, then possibly I could simplify those away or reduce them away in that case. So let's think about that. In my first step, I'm going to keep 2 root 5 the same on top. On the bottom, I want to think of this as, well, 180 could be broken up. Can it be broken up into 5 times something? Or in other words, something times 5. Can 180 be broken up in that way? Well, yes, because obviously it's a multiple of 10, and every multiple of 10 is also a multiple of 5. So it must be divisible by 5, and if I divide it by 5, I get 36. So 180 is actually 36 times 5, which means, again, I'll rewrite the top, but the bottom is like root 36 times root 5. Before I do any simplifying overall, I can simplify the bottom even more so into 6 root 5, and suddenly I have a common factor on top that can be divided and something on the bottom that's equivalent to it that can be divided as well. So I divide both the top and bottom by root 5. In other words, I'm essentially reducing it by reducing a common factor or dividing both by a common factor, and I get 2 over 6, which is really 1 over 3 when I eventually am able to speak correctly. So 1/3 is what that would simplify into, which means the radical parts have actually simplified away completely. And now let's try and do something similar for this one, except in this case, the radical that I do have on top is 216, and that means I can try and, if possible, divide it nicely with something on the bottom. And in this case, it actually does divide nicely with the radical on the bottom. So when this occurs, you can think of it as essentially dividing the number parts and separately dividing what you have inside of the radicals. So -10 divided by 2 tells us that we're going to have a -5 coefficient in front of this whole thing. And then I'm going to just sort of skip a step here and say 216 divided by 3 is 72. So it's really like root 72 because I divided, and I'll just make a little note there. So I divided those, and then the answer is what I put into there. But now 72 can be broken up even further. So I can call it -5 times, well, let's say 36 times 2. And why did I choose 36 and 2? Well, because 36 is a nice perfect square number. So it's really -5 times an extra 6 times root 2. And now in this case, I already had a coefficient of -5, but now I ended up with this extra coefficient of 6, and everything is squished together, which means the first two pieces are just regular old numbers that can be multiplied together. The radical, though, can't be multiplied with those. So the radical just sticks off the end, almost like it's a variable attached to it. It can't be combined with the coefficients or the numbers itself, so we just get -30 root 2. From here, let's look at the rules for multiplying radicals and then put everything together to try and simplify some additional situations. So here, when we are multiplying, it's as simple as thinking of multiplying the number parts together, the regular number parts, the coefficients together, so 2 times 5. And then we're separately going to multiply the radical parts together, 3 and 6. So overall, think of this as doing like 2 times 5 times a root 3 times a root 6. The 2 times 5 part is going to be 10. Oops, I was thinking ahead there. 10, and then the 3 times 6 part is where the 18 is going to come in. So it's root 18. Root 18, though, and I'll maybe start skipping the step of writing the two things multiplied inside, and I'll just write this as root 9 times root 2. Or in other words, it's like 10 times 3 times root 2, or really just 30 root 2. Let's try another one now. A little bit quicker. So now we can just, without writing that extra step, I can just say 9 times 4 is 36. And then it's going to be the square root of, well, 2 times 14 is 28. So square root of 28. Well, 28 could be broken up into 4 times 7. So it can be broken up into those two separate radicals. Or it's like 36 times an extra factor of 2 times a root 7, because the square root of 4 can become 2. Or it's really like I have overall a coefficient of 72 times root 7. And one more of this type. 3 times 5 is 15 times the square root of 49. Well, actually, in this case, we don't have to break 49 up any further because 49 itself is a perfect square. So it's really just 15 times 7, because that's the square root of 49, and 15 times 7 gives us 105. So that one just works out to a single whole number with no radical piece attached. One last little section is going to allow us to see some additional types of simplifying we can do with certain types of radicals. And it's going to come back to a little bit of review of factoring. Specifically, common factoring is really important. So in this one here in question A, there really isn't any simplifying we can do with any of the radical stuff involved. But there is a radical as part of this expression, and there is still some simplifying we can do with this expression. We can actually take everything we see on the top of this expression and common factor out a 7, because this is essentially one piece or one term of our numerator, and it can of course be divided evenly by 7. This overall is also a separate term in our numerator, but it can also be divided by 7, because really what I'll be doing is dividing its number part or its coefficient part by 7. And I won't need to do anything with the radical. So it would be a 7 that I pull out in front, and it becomes 3 minus 2 times root 6. So you can see the root 6 is really acting just like a variable that I would have had. So if you can imagine, if I, back in our simplifying rationals lesson, had given you something like 21 minus 14x over 7, well, you would realize that that stuff on top can factor out a 7 as 3 minus 2x. And so the common factoring of the number has a lot to do with how it's going to change the coefficients, but that x that would be attached to the coefficient doesn't change. That's how the radicals are going to work as well. They're attached to whole numbers in the same way that a variable is attached to a coefficient, but they can't be combined in the same way or factored out in the same way, so they just essentially attach along for the ride, just like a variable might. So that's just a little aside there. But where I was really going with this, what's more important to notice is that now I can divide the top by 7 really easily and leave a factor of 1, which is nice because I can divide the bottom by that as well and leave a factor of 1 there, which means these 7s are really actually going to disappear because they've been reduced to 1. So I really just have 3 minus 2 root 6. That's the simplest way I can write that. And notice I don't have to write any restrictions for this because the denominator can't ever be 0. The original denominator was just a 7, and it can never become a 0. It's always just going to be 7, even when it's reduced away. Let's try another one now. Well, in this case, before we try and do any overall reducing using common factors in the tops and bottoms like we did in our last one, always try and make sure that your radical expression is as simple as possible first. So we'll first use the skills that we learned at the beginning of this lesson to tackle root 45. So I'm going to call this 6 minus root 9 times root 5. And the whole thing's over negative 3. Or in other words, it's like 6 minus 3 root 5. And again, the whole thing is over negative 3. As soon as I get to that stage, now let's think about what we just did in our last example and realize that we can try and common factor on top once again. So both pieces on top can be divided by 3, or common factored with 3, to leave 2 minus root 5. And that whole thing is over negative 3 still. And now I'm going to reduce away the 3's, but also keep in mind that when there's only a negative on the bottom, but no negative on top, in my final result, I want to switch that around so that the negative is in the numerator and not the denominator. So instead of just dividing the top and bottom by 3, I'm actually going to divide the top by negative 3 to leave a negative 1, and divide the bottom by negative 3 to make it positive 1. So what do I actually get there? Well, suddenly I have a negative, and I should be careful here, I have this negative 1 that then needs to be expanded or multiplied by each of these terms. So my numerator that I have left is really negative 2 plus root 5. And I don't need to write anything in my denominator at all. Let's try one more. So now, once again, we'll follow the same steps, and that root of 125, that radical, we're going to try and break that down first, and then do common factoring or anything else we can from there. So this is going to be 2 times, I'm going to break it down into root 25 times root 5. And the whole thing is still over 10. So it's really negative 15 plus 2 times 5 times root 5, because root 25 can be square rooted. A little bit simpler, that'd be like negative 15 plus, well, 2 times 5 is 10 root 5, all over 10. And now everything on top can be divided or common factored with 5. So it could be, for example, common factor the 5, and we would have negative 3 plus 2 root 5 left over, and 10 on the bottom. And why was it important to common factor that 5? Well, hopefully you can see that now it can be reduced with what we have on the bottom as well. So I can divide the top by 5 and leave a 1, but then I have to be very careful. I'm dividing the bottom by 5, which is actually going to leave a 2. It's going to still leave a factor of 2 on the bottom. So really, overall, it's like negative 3 plus 2 root 5, and I can't forget that's all over 2. So take some time, make sure you get lots of practice working with these and understanding these basic skills in terms of working with radicals. And as you're hopefully seeing along the way, in a lot of cases, when we simplify and combine these with other terms, in a lot of cases, the radicals end up behaving a lot like variables would when we combine or simplify things that are like terms. We're going to use those skills a whole lot more in our next lesson, which is really just going to be a follow-up to this and continue seeing how we can use operations that involve radical expressions.